Good afternoon, everyone. Welcome to the CERIAS Security Seminar at Purdue University. Today's speaker is Qihua Wang. Qihua is a third-year PhD student in our department, and he will be presenting two papers next week at the ACM conference on computer and communication security, which is one of the top conferences in this field. And today he will talk about one of those two papers. Here's Qihua.
Yeah, thanks, Professor Lee. So today I would like to introduce an algebra for specifying high-level security policies. And this is a joint work with Professor Lee. Not yet. And the paper reporting these results will be presented in this year's CCS. And as you can see, there's in the topic of the paper, we have beyond separation of duty there. So what is separation of duty? Separation of duty is a principle that it's not in the yeah, but if we change it to full screen, it just jump to the third slide. So I'll wait until I reach the third slide. And separation of duty has been widely used in the physical world, and actually such a principle exists long before the information age. For example, in the two-man rule, it states that no single person can launch a nuclear weapon, and a nuclear weapon can be launched only if two qualified people agreed on the command. And in its general form, a separation of duty policy requires that at least k users to complete a task. However, it does not restrict which user to perform which steps in the task. In this case, separation of duty is a high-level policy that states an overall requirement for a sensitive task. So although separation of duty policies are very popular, there are limitations for separation of duty. Especially a separation of duty policy states only quantitative requirement and does not express qualification requirement on the set of users that perform a task. For example, we may want to have 3 users to finish the task, and in addition to that, we may want the set of users to contain a manager and 2 clerks. And so separation of duty does not specify such a qualification requirement. So existing approach solve this problem by specifying the qualification requirement at lower level. For example, the task may be partitioned into 3 steps, and we may require that the first step be performed by a manager and the clerks to perform the next 2 steps. However, specifying the qualification requirement at low level lost some benefit that are offered by high-level policies. For instance, high-level policies abstract away the details of how a task is implemented. High-level policies are more close to organization policy guideline, and it is easier for the administrators to design and understand high-level policies. Furthermore, high-level policies can be specified even before the design of actual steps in the task comes out. And actually, having formal specification of the policies can help the design of the steps to implement the task. And finally, using high-level policies allows the flexibility in the choice of enforcement mechanism. We can choose to enforce the policy either statically or dynamically. And since there are lots of advantage for using high-level security policies, we would like to have a language to concisely specify high-level policies. That's why we introduced the algebra. And before formally introducing the syntax of the algebra, I would like to show you some examples of terms in the algebra. In the first example, the term use operator O times to connect three keyword OR, and such a term requires that exactly three users to satisfy such a term. And the second term use the operator square cup. The operator square cup is analogous to logical OR. It means that a user who is either a manager or an accountant can satisfy a term. And the third term use the operator square cap and a negation operator. It means that a manager who is not Alice or Bob can satisfy a term. And the fourth term use the operator O dot. It means that a manager and a clerk can satisfy a term. In particular, if one user is both a manager and a clerk, that single user can satisfy this term. And in this differs from the last example. The last example used O times to connect the manager and clerk, and such a term requires two different users to satisfy a term. So even if one user is both a manager and a clerk, he does not qualify. And here's the syntax of the algebra. And an atomic term in the algebra can take one of the three forms. It can be either a row, the keyword or a set of users. For example, in the third term, Alice, the set Alice or Bob is an atomic term, which is a set of users. And the algebra contains two unary operators and four binary operators. The two unary operators are negation and closure. And in order to make the security policy expressed in our algebra to have a clear meaning, we place a restriction on the use of the two unary operators. Okay, and then we go on to introduce the semantics of the algebra.